Cool. So that's recording locally here. And then I'll slice it so it's the beginning of your, your beginning of your proper presentation. Once
So you'll do the post-processing.
Yeah.
And greetings to the others that are joining us. We'll wait a few minutes for some more to come in, and request that everyone mute their mic.
In the lead up to it, we always start the main talk 5-10 minutes late because it takes a little while for people to roll in. So in the meantime, if anyone has anything fun they've been working on, or questions, or just general comments on the weather, feel free to shout out.
Also, participants can use the chat window to ask questions and whatever. I'm Barry Duggan, organizer of this event, and co-hosting with Derek Kozel. And I'll talk a minute about GRCon 21. That is our annual conference meeting, be held in Charlotte, North Carolina, September 20th to 24th. Everyone is invited. If you can't do an in-person attendance, you can attend by virtual at no cost, or we request that you make a donation to help defray some of the expenses. And that will get you the streaming for the whole week. And then if you want to participate in workshops, there is a $50 fee for that. The advantage of attending in person, particularly if you're somewhere close to Charlotte, you'll be able to see the exhibits and talk with the sponsors and talk with the other attendees. A lot of interaction there and lots of things to learn. Even though I'm on the organizing committee for it, it will actually be the first GRCon that I will have attended. It was held here in Huntsville 2 years ago, and I was able to go to the Thursday night social and meet some of the people, including Derek. But this will be the first year that I do a full conference. And I'm also doing 3 presentations during the conference. Does that amuse you?
There's a sure sign that you haven't been before. 3 presentations is definitely a full workload there.
Well, they're going to be spread out. I'm going to do a lightning talk, which is 5 minutes on Monday. And then I'll do that. I'm doing 2 things at once here. I'll do the Friday breakout session for the amateur radio group. And then sometime midweek, I'll do a half-hour talk on my station control program, which should be fun. And
yeah, we've been reviewing and accepting talks for the conference over the past couple weeks. So a few of the acceptances are a bit late going out, and the whole schedule is yet to go up, but the lineup's already starting to look much as it has in previous years. You know, a whole bunch of talks, some workshops. Hopefully we can get those posted really soon, because that's definitely, you know, fun to see. Always fun to see.
Well, it's 4 after, and we got 16 people so far. Why don't we go ahead and do introductions? Barry Duggan, KV4FV. I'm the organizer of this group. I'm also the documentation lead for the GNU Radio Wiki, and got into that a couple of years ago. Been a ham since 1953, electrical engineering graduate, but programmed all my life. Derek, brief
Hi.
word.
Derek Kozel, K0ZEL in the States, because I couldn't possibly miss up that opportunity. MW0LNA here in Wales, where I live. I also one of the GNU Radio leads. I got into all of this because of amateur radio during my undergraduate. So big thanks to the W3VC University Club. And yeah, I'm super excited that this keeps running month after month. For the folks joining in late, we are looking for future talks and also future coordinators. So please put your name in the hat or in the chat if you'd be interested in helping out in either of those ways. And then we have the star of tonight's show, Tom. Why don't you give you a quick introduction yourself?
Good day, or good morning, or good afternoon, whatever it is. My name is Tom McDermott, N5EG, and I've been a ham for about 50 years. My background is I have a degree in electrical engineering and worked on high-speed fiber optic transmission systems for most of my career. So with that, let me see how I share slides here.
There's a share screen
Okay.
down there. You see it?
Yes, I do. Okay, so let me do desktop, and
You're live.
Ubuntu.
do we have slides?
You do. Go
Okay,
for it.
well, that's a good sign. Having slides is always good. All right, so this presentation is titled Using GNU Radio for Some Amateur Radio Measurements. I got started in GNU Radio in 2012 when I attended the DCC, and there was a Sunday seminar on GNU Radio. The intention was to build a program to do ionospheric echo sounding, and I ended up writing a driver for the Open HP SDR radios, which seems to be well received. Used that to do echo sounding, and that was presented at the DCC 2015. And those measurements were successful in being able to range and measure Doppler shift on F-layer echoes. One of the things that struck me is that GNU Radio has an incredible amount of measurement capability built in. And so for amateur radio use, you can get by with a minimum amount of hardware equipment if you use some of the measurement capabilities built into GNU Radio. And that's kind of what I want to talk about today. So on this talk, I've got a few measurements set up. One is to measure receiver noise figure. Another is to find the dBFS, or the maximum ADC input signal range and the offset. Look a little bit at receiver dynamic range measurements. SDRs pose some differences compared to analog receivers. Look at spurious components in SDR receivers, and then look a little bit about scalloping variation in FFTs and window functions, and discuss those. So one of the key things in measuring the receiver is measuring the noise figure. As hams, we're used to measuring sensitivity, But usually a more common way to measure that is through the noise figure of the receiver. The method used in this test is to connect a calibrated noise source. The noise source I happen to have is a 5 dB excess noise ratio source. It's a Zener diode biased up, and then it runs through an attenuator. To do that, the noise source is connected to a receiver, and then there's a switch on the receiver where you can measure a 50 ohm resistor. And so by flipping that switch back and forth, you can see how much the noise level increases when you go from a 50 ohm resistor at room temperature to the broadband noise source. That difference is called the Y factor. That's the increase in noise in dB when the noise source is enabled. And I describe it here as the noise source turned on. Inside the calibrated noise source is about a 20 dB attenuator. And so rather than actually having a switch, I just turn the power to the noise source on and off. And it basically gives the same as though we had a switch between the noise source and the 50 ohm resistor. So I'll alternately describe it as turning the noise source on and off, or switching back and forth to the reference resistor. So the equation for noise figure is to look at the increase in noise between the resistor and the noise source. And that's plotted in the graph here, where on the x-axis is the measured Y factor in dB, and on the y-axis is the noise figure of the receiver. The key point here is we notice that when the Y factor is 3 dB, that the noise figure measured on the receiver is 5 dB. That is the excess noise ratio of the source. So if our receiver had a noise figure of 5 dB and we had an excess noise ratio source whose ENR was 5 dB, then when we turned it on and off, the Y factor, the receiver noise, would go up by 3 dB. So the flow graph here is to look at the output of the receiver and look at its noise. This is the actual measurement. We've down converted the receiver, and in this case, the frequency is about 29.5 megahertz is the center of the band. We're looking at about 48 kilosamples per second. The FFT bin size is 2048 samples, and that makes each individual FFT bin about 23 hertz wide. The display in GNU Radio uses exponential averaging set out to about a few seconds. And the Y scale here on this measurement is 2 dB per division. So the way the measurement is run, and the noise source is turned on, and the maximum hold button is selected on the display, and that gives the green curve. And then the noise source is turned off and the max hold is turned off, and you get the blue, which is the average noise. So the difference between those two is approximately the noise increase by turning on the source. It's not exactly, because the green line is a maximum rather than an average hold. And GNU Radio doesn't have a way to hold the scale. And so this is kind of a poor man's snapshot. Better, of course, would be to have a previous trace and a current trace, and then display both of those. And this is sort of an approximate way to do that. You can see the difference between the two is about 2 dB. And so 2 dB per division. If we go back to the previous slide, the Y factor is 2 dB. We go up to the point and we can see that the received noise figure is about 7 or 7.2 dB. So at 10 meters, the noise figure of the receiver being measured here is about 7 dB. Simple measurement to make, and fairly easy to do. By tuning the receiver to different frequencies, you can measure that noise figure at different frequencies. So the next test is to measure the ADC maximum input level. And the way that's done is to use the wideband receiver. So in OpenHPSDR, there is a mode where the receiver can run wideband, that is not received down converted by the FPGA, but just the raw ADC samples. And so in this case, there is a signal generator put into the Hermes wideband receiver. And that wideband receiver, which is just the raw 16-bit samples, goes into a vector to stream conversion block. The Open HB-SDR receiver puts out 16,384 samples and then a bunch of dead time, and then another 16,384 block of contiguous samples. And so the Hermes wideband receiver module is a vector of 16,384 time contiguous samples and then a bunch of dead time. The reason it works that way is that the 122.88 megasample per second clock rate of the Hermes, the output sample rate is much, much faster than the 100 megabit Ethernet available. And so by putting out a burst of samples and then having dead time and then another burst of samples, the samples can be output at 100 megasamples per second with the proviso that there's a dead time in between them. The vectors are converted to a stream, and the stream is then input to a time sink. So these are two screen captures that didn't get the time exactly the same there. But on the left side, you can see that the ADC is going into clipping. You can definitely see the clipping. The clipping is at a value of plus 1.0, and the ADC scale factor on the Hermes wideband is minus 1.0 to plus 1.0. I then inserted 1 dB additional attenuation into that signal, and you can notice that the output samples come down off of the positive rail, and you can see they're now point-like in the right-hand graph rather than clipping. And there's some slight variation that's actually aliasing, in that at 122 megasamples per second, we get there's some slight phase difference between the generator and the clock in the receiver. And so it doesn't digitize exactly at the peak of the signal. And so you'll see some slight variation. So we go ahead and find the point where we slightly clip, add in 1 dB reduction. If I had an attenuator with less than 1 dB steps, I would have used less than 1 dB reduction. But the best attenuator I had 1 dB steps. Then once we take it down, we actually disconnect the generator from the receiver. We put it into an oscilloscope. We measure the voltage, and that voltage is the full scale voltage of the receiver. Another measurement that we can take is to disconnect the signal generator from the receiver and connect it up to a 50 ohm resistor. So there's essentially no signal going into the receiver. And when we do that and we zoom into the scale on this particular receiver, we see that the dead signal there is at about minus 2 millivolts. And so that means that the A to D converter in the receiver has a minus 2 millivolt offset voltage. And that represents on a -1 to +1 scale about 64 counts of offset on 16-bit converter. So we have something that's about 30 dB down from full scale is the ADC offset voltage. It's about 27 dB down. And that's an important number, as we'll see in a later graph. So we now know the offset voltage, we know the dB full scale, and we can use that to make some additional measurements. So having those as baseline, then we can start to measure dynamic range of the receiver. Third order dynamic range in SDR receivers is a little bit of a challenge. An analog receiver has a pretty well defined methodology for measuring third order, and that's to measure the third order intercept point. An SDR receiver doesn't have a third point intercept the same way that an analog receiver has. And so intercept point measurements are not very meaningful for SDRs. So what instead I did is to measure the third order IMD product using GNU Radio compared to dB full signal. And I needed to end up turning the preamp that's built into the Hermes SDR on and off in order to get a sufficient linear measurement range to measure all of these. And what I did was to build well, let's go first and define what is third order. If we have two signals, F1 and F2 in the center of the graph here, two carriers, when we increase those to some level, we'll get third order, fifth order, and seventh order products, which are the 2F1 minus F2, 2F1 plus F2, 3F1 minus 2F2, 3F1 plus 2F2. Those will give all the odd order products. And there's a couple of even order products, F2 minus 1 and F1 plus F2, which are way outside the spectrum band. For example, if F1 and F2 are near 10 megahertz, then F1 plus F2 will be at 20, whereas 2F2 minus F1 will be at about 10.001 or 10.002. In a traditional analog receiver, and these slides were produced by Adam Farson, VA7OJ, who's got a great website and has done a lot of testing, is that in a traditional analog receiver, the blue line is the signal level of the two signals that we're trying to inject to the receiver, for example, at 10 megahertz and 10.002 megahertz. As we increase those signals, the red line is the third order intercept. So if the two generators, F1 and F2, were 10 and 10.002, then the third order would be at 10.004 and 9.998. Those signals increase for third order products 3 times as fast as the increases of the signal. And so we can see that if our receiver didn't go into compression, that we can plot the intercept point of the red line with the blue line, presuming we didn't have compression. And that would be the third order intercept point of the receiver. The higher that point is, the better the analog receiver is at not having artifacts from the receiver. We can see in an SDR receiver that, in fact, the third order products are kind of independent of input power. The red line goes up slightly faster than the blue line until we get to dB full signal, and dBFS 0 means where the ADC on the receiver goes into clipping. So we can't produce any output related to the input higher than that because we've actually reached clipping. So in order to do that, I'm going to skip ahead one slide and then back up. The way we do the measurement is we have the two generators. They need to be two very clean generators. Those are put into a combiner through a step attenuator and into the receiver under test. In my case, generator 1 is a rubidium oscillator, which is 10.0000 megahertz. And generator 2 is an HP 8640 generator, which is a very clean analog generator. Those two go into a combiner and then the attenuator. There's a couple of different kinds of combiners available. I used a resistive combiner, which is probably the worst possible choice, but the junk box yielded 3 resistors of the correct value. And so by definition, that was the test equipment selected. The way that that's done is there are 3 16.7 ohm resistors connected up. Generator 1 and 2 each feed a resistor. The output then feeds a 50 ohm attenuator. The purpose of the resistors is to impedance match. Generator 1 sees 50 ohms, generator 2 sees 50 ohms, and the output looks like a 50 ohm source impedance when you connect up the resistors this way. So the advantage is that you get good broadband impedance matching with this kind of a combiner, and your junk box may yield the correct parts. The significant drawback is that generator 1 and generator 2 can, in an analog fashion, talk to each other through the combiner, and you'll see that's in fact one of the problems in my measurements. Better is a Wilkinson combiner, and that is where generator 1 and generator 2 feed a 100 ohm resistor that goes between them and a quarter wave transmission line, in this case 70.7 ohm coaxial cable that's a quarter wave long. And if those then feed a 50 ohm output load, for example, a step attenuator, then generator one, if the transmission lines are the right length and all the impedances are correct, will null into the generator two output. Generator two will null into the generator one output, and both of those will sum into the output. So it provides much better generator to generator isolation. It's fairly inexpensive. It is frequency dependent because the transmission lines only produce a 90-degree phase shift at the frequency of interest. And we're reliant upon the two transmission lines producing 180 degrees of phase shift so that those signals are out of phase with the signal from the 100 ohm resistor, resulting in cancellation. You can also substitute an inductor capacitor LC quarter wave section for the transmission line, as long as that LC produces a 90-degree phase shift. And then it's a lot more compact than having to coil up the transmission line. It can be somewhat broadband if instead of transmission line, you use transformers that are of the right impedance step or step down ratio. And so you have to have some transformers of the right impedance ratio in the jump box. And so I didn't have either the transmission lines or ratios. The best approach is to use an active buffer amplifier. And in that case, you have generator one feeds an amplifier, generator two feeds its own amplifier, and then you can resistively combine those. Those PAs need to have good reverse isolation. And so those are kind of a special breed of amplifier. They don't need a lot of output power, but they need good reverse isolation. So going back to the measurement here, I used the quick and dirty approach, which was a resistive combiner. And the measurement made was to set the input level of the carriers and then step up the output of that attenuator that's after the combiner. That's the red line on the graph here. You can see the next line down, the orange, is generator-induced spurious. So no matter where I set that attenuator, I got a spur that was 30 dB down from the input level of the carriers. And that turns out to be the rubidium oscillator being modulated by the HP8640B. And the level of modulation is independent. If we go back here, you can see generator 2, the 3860 is modulating generator 1. And that level of modulation is constant in the combiner and independent of the level of attenuation. So it's down at a 30 dB down level. I then measured the third order intercept level. It's not actually the intercept, it's the third order intermodulation product. My mistake, the third order product. And here you can see that that third order product is relatively constant over a fairly large range of input signals. And once we get up to near the ADC clipping level, then that third order product suddenly starts to increase. When we get to the input level of the carriers being about a few dB below the clipping level, their maximum peak summed in phase will hit the clipping point of the ADC. And then as soon as we get the clipping, those output, we get third order products that suddenly shoot up, and that's where the gray curve turns up. On this particular receiver, that happens at a level around S9 plus 90 dB on the converter. The clipping level on the converters in the receiver is S9 plus 92 dB. So as we back those down, we see that the input carriers go down, and as we go down to the left, the third order intercept products continue to decrease. For reference, the yellow line at the bottom is the average residential noise level at 10 megahertz from the CCIR radio noise specification. And so we can see that for most of the dynamic range of the receiver, the third order products or at or near average residential noise level. And so those products are higher than in typical analog receivers, but they're by and large not significant because they're pretty much at the noise level. And then once we get down to about S9 plus 30 dB for the input signals, that the third order IPs kind of drop below the noise level. So for most practical cases, software-defined radios have pretty good intercept performance. And it's when you start to get to about the 30/9 level of the two interfering signals that you can start to see the intermodulation products creep above the noise level. These measurements were taken here with a 2.5 kilohertz spacing. Another important point is the spurious component. So most SDR receivers aren't perfectly clean, and they generate some internal spurious spectral components unrelated to the signals that are coming in. The way that these were measured here was to use the wideband sampling mode of the Hermes SDR. That was, so they used the wideband mode, and the OpenHB SDR has this rather unique wideband mode providing 16,384 time contiguous real samples, and then a long dead time, and then repeat. And that's again done so that the 100 megabit per second Ethernet connection on the receiver can handle the sample rate. It would need something in excess of a gigabit per second if it were in fact a real-time wideband sampling mode. The way the measurement's made is we do a fast Fourier transform on that block of samples, and the FFT is locked so that the first sample of the 16384 block is input to the FFT, the last sample is blocked, and then the FFT does a conversion. Then there is a window applied to the FFT, and that window is done because there's a big sampling discontinuity. Because we have 16,000 samples in that dead time, and those 16,000 samples are not phase locked to the FFT, we get a very big discontinuity where if we were not to window, we'd see what looks like a big phase jump. The input signal would have a big phase jump because it's not phase locked. We then filter the FFT output bins, and we filter them with 8,192 IIR filters. And that allows us to reduce the noise level by integration over time. And then we can display that with a vector sync. So we have the sample rate of the receiver is 122.88 mega samples per second, divided by 16,384, means that the FFT bin size is 7,500 hertz per bin. So this is the flow graph that we use. The Hermes wideband receiver is connected to a 50 ohm receiver, which is basically a BNC connector with a 50 ohm receiver or 50 ohm resistor in it. It's running the wideband mode. That dark brown means that that's a vector mode on the Hermes. The GNU radio color codes the samples, and they're kind of an orange color for real samples, and they're kind of a brown color for a vector of real samples. So that 16384 vector goes into an FFT, which has its vector size of 16384. The FFT outputs samples, and those are in real mode. There is a vector to streams block in GNU radio, and that vector to streams block is set to output two streams. And it turns out, because the FFT is a real FFT, we get a mirror image. We can't distinguish negative frequencies coming out of Hermes for positive frequencies. And so the output of the FFT is mirror symmetric. So the vector to streams outputs the first 8192 vectors, and the second 8192 vectors go on the other output. So we send the second set of vectors to the null sink, because they're just a mirror image of the samples that we care about. Those then go into a single pole IIR filter. And this is set up for a vector of 8192 because the vector block size coming out of the vector to stream converters is 8,000 samples. And so what this does is this gives us an array of 8,000 low-pass filters in one block. Extremely convenient. That particular block in GNU Radio, I've used time and time again because it's capable of implementing the 8,192 separate low-pass filters in one block. We then take that vector of samples and we compute the magnitude. And so we compute in 8,192 independent magnitudes, one per sample in the vector of samples. We take the log to get dB, and then we output that to the GNU Radio vector sink, which is a type vector as well. So this is what the output of that receiver looks like. And we can see we go from the 0th FFT sample up to the 8192nd FFT sample. And the units are 7.5 kilohertz per sample. The GNU Radio vector sample does not have a way to change the labeling of the frequency axis. They're just vector counts. And so you have to mentally do the arithmetic in your head that 8192 is equal to 61 something megahertz. And what we see here is on the left side, the big spike is the 0th sample. That's the DC component of the A to D converter. And so that's essentially the offset voltage of the A to D converter. And we can see that's about 23 on the scale. Recall that that was about 2 millivolts. And so full scale of the converter would be about 50 dB on this particular 2 millivolts is about 27 dB down from full scale. So the top of the scale at 50 dB is about full scale of the converter. And so this has been set to do an integration. The alpha is set for 0.0007. That's the slider on the top, and that controls alpha into the block. And when we do that, and then we twiddle our thumbs for a couple of minutes, we see the noise components slowly integrate down towards 0. Because noise is random, the integration of noise tends towards 0 over time. What does not tend towards 0 are the periodic components, those that repeat on each sweep. And so that causes the spurious components to sort of not diminish over time. The spurious components emerge with time out over the background noise. And so we see that we have a couple down here at low frequency. And what those are local AM broadcast stations linking through my 50 ohm resistor and 50 ohm connection into the receiver, getting in through the DC power leads on the receiver. So there's some things there that are pretty difficult to get out of the receiver. And we have a couple of multi-kilowatt AM stations about a mile away. And so those are pretty strong. Then we have some significant digitizing components marked further up on the scale. And those are actual digitizing artifacts present in the receiver. So we can see that we have a number of samples down in about the minus 100 dB FS. And we have a couple of spurious artifacts that are a little bit above 100 dB full scale. The one down here at 2,800 samples is around 12 megahertz. And we can see that it's about 15 to 20, it's about 15 dB above minus 100 dB, so about minus 80 something dB full scale. One of the common misconceptions that a lot of folks have is that the signal to noise ratio of the A to D converter is the same as the dynamic range of the converter. And that's not actually true. The signal to noise ratio of an ADC is related to the quantization noise of the converter. So the 16-bit converter in the particular receiver that's being tested here has a 12.6 effective number of bits. So the manufacturer specs that 16-bit converter for 12.6 ENOB, or effective number of bits. And the signal to noise ratio of 12 bits is given by 1.76 plus 6 dB times the effective number of bits. So for this converter, that would be 77.6 dB. The signal to noise ratio is the maximum signal compared to the quantization noise in the ADC's Nyquist bandwidth. So the Nyquist bandwidth in this test is 61 megahertz, which is the ADC clock divided by 2. And so the signal to noise ratio of the converter is 77.6 dB. But we can see by this chart that we can easily see spectral components down below 76 dB, below the full scale. And that's because we are integrating those over a large amount of time. And so we're looking at the noise in ever decreasing bandwidths. As the low alpha filter integrates the noise, we're looking at noise that's been integrated over time. And another way of saying noise over time is narrow frequency bends. So in fact, the dynamic range of an ADC is quite a bit better than the dynamic range just looking at the signal to noise ratio by effective number of bits. So the ADC manufacturers will specify what they call the spurious free dynamic range, or the SFDR. And in the ADC, that's done by measuring the full scale signal and then integrating the daylights out of the noise until the noise drops way down. This particular converter has a specification of 100 dB SFDR. I shouldn't say that too quickly. And anything that's worse than that is a receiver implementation degradation. So if we go up to this chart, minus 100 is down about near the receiver leakage. And you can see a bunch of noise components. There's a couple of components that leak up above minus 100 dB due to artifacts in the ADC. And there's one or two that leak up above that, and those are due to receiver implementation artifacts. And then, of course, the ADC offset voltage, which jumps way up off the screen. So the last topic is what is called FFT scalloping. And this is an interesting thing when you're trying to measure the absolute value of components, is that there'll be another error introduced depending on where the component sits with respect to the FFT center frequency. And these charts come from an excellent article by Richard Lyon called Reducing FFT Scalloping Loss Errors Without Multiplication. And what he did was to show how in an FPGA you could normalize this using adders only in an FPGA and not having the result of multiplication. And of course, if you can avoid multiplication in an FFT, you reduce the amount of signal processing needed. So in the upper left, if we look at the blue lines are the frequency response of an FFT bin versus the frequency put in. And there's a number of these for adjacent FFT bins overlapped. So the bin on the left that's labeled A minus N over 2, if we take a single FFT signal and we slowly sweep it across a single FFT bin, when we get that sine wave dead on the center of the FFT bin, we'll have the maximum signal. If we move that signal to the maximum of the next adjacent FFT bin, we actually get a 0. That sine wave has a null in the next FFT bin up. So for example, if it were 1024 hertz and the FFT bin was a 1024 size in relation to the center frequency normalized, then at 1025 hertz, we'd get a null in the 1024 4 hertz bin. That's because at the bin size, the FFT bins are orthogonal, and so we get a null. And so the 1025 hertz signal would have a maximum at 1025. It would null at 1024 and null at 1026. And so that's what this chart shows, that you get nulls. Now, what happens when you sweep a signal across is that as it nulls the 1026 bin, it'll actually have some signal in the 1027 bin. And so if you look at the signal as you sweep a sine wave across an FFT, you'll get the lower part of the left-hand figure, marked figure 1, as a signal goes up to the bin center, goes down, and it doesn't get a chance to go down to 0 because it starts to now emerge in the next FFT bin up. You'll see that a sine wave signal amplitude will go up and down as you sweep it through the FFT bins. And this is what Lion calls scalloping in the FFT. Now, if you have, and looking at figure 2, if you don't use the window at all as you sweep a sine wave across, then you get the scalloping response marked rectangular. And so in this case, the left-hand side is when the sine wave is right on the center of the FFT bin. The middle is when it's halfway between 2 FFT bins. The right is the center of the next FFT bin. So you'll see a drop off in amplitude. If we use different time windowings to get rid of the discontinuities, the Hamming window, the Hanning window, and then up at the top, the flat top, you'll see that the scalloping error is less between the various type of window functions as we sweep a sine wave. The flat top window, we can see there's no variation in the signal amplitude as we sweep it across. And that's why, in fact, that kind of window is called a flat top, because the response is flat across the varying windows. So what I'm going to do here is try to bring up this, and I was having problems with this not coming up full. There we go. Okay. So what this is a flow graph. I have a signal generator. Well, let's go back to the flow graph here. We have a signal source with very fine resolution on a slider. It goes through a throttle. Then it goes in 2 frequency sinks, one with no window, that's the rectangular, and one with a flat top window. And if we run this, what we'll see is the output of each of those set. Now let's zoom in here. I'm going to zoom into the upper window here, and I'm going to zoom into the lower window. And we see, let's turn on the grid. And let's turn on the grid here. And what we see in the top is a rectangular. And as I slide the slider for frequency, and we slide this around, and I can't grab it because it's directly underneath the my window here. If we grab the slider and I slide the frequency, you'll notice that the peak, as we get to this point here in the rectangular window, right here, we've got the peak directly centered on the FFT bin, and then this is that sine wave in the next FFT bin. And if I now put that FFT bin kind of halfway in between the two, so this is where the sine wave is now in between these 2 bins, the peak amplitude is less than it was when it was directly into the maximum, where the sine wave is right in the middle of the FFT bin. So if I do a max hold here and I sweep it, as we sweep the signal, you can see right here, this is the maximum and this is it when it's half off. The bottom signal is the flat top signal, and you'll notice as we slide it, that no matter where we put the signal amplitude, as we slide it across, the amplitude is constant. So if we then do a max hold on this one, we can see there's always a signal sitting at the maximum of the bin. So one thing that you have to be cautious of when measuring amplitude is that you know the relationship of the FFT signal that you're trying to measure compared to the actual FFT bins. Now, an interesting thing happens in GNU radio, and that is that the standard GNU radio windows do not have the same gain. So the flat top gain is different than the rectangular gain, is different than the Hamming and the Hanning gains. And so I put together a chart here where what I did is I had a frequency source, and this is all done in simulation, and I swept it much as we did the previous one between the lower FFT bin edge and the upper FFT bin edge, and then measured the amplitude. So the signal source had an output of 1.0, and so that would be a 1 volt signal source. And we can see for a rectangular filter, if the frequency is exactly the FFT bin center, the output of the FFT measures 0.0 dB, that is full scale or 1 volt. And as I sweep that signal from the lower edge of the FFT bin up through the center to the down, we get about 4 dB of amplitude variation, which is what we expect from theory. If I then use a Kaiser window, which is the orange line, there's less pronounced amplitude variation. It goes from -7.9 up to -6.8, or about 9/10 of a dB, down to 7.9. A Blackman-Harris window has a little bit less variation, and the flat top window, the amplitude is the same at all bins. It's -13.33. But you notice that the center of the bins are different for all the different filter functions. And in Lyon's paper, what he did was to normalize all these bins to 0. So that if you chose, for example, a flat top filter and you happen to hit the center of the bin, then the flat top would output an output of 0.0 dB rather than an output of -13.3 dB. So Lyon's approach is to normalize all these filter windows when in the center of the bin to 0. And then of course you still get amplitude variation off to the edge. And this threw me for a loop in a lot of different cases when trying to make measurements. I always got a measurement of -13 dB, and that rather than the variation that you would see here in this particular window. It's not to say that Lyon's approach at normalizing at the centers is correct, or that in fact any particular amplitude is correct. It's just the particular way that he chose for doing this. And so if you're going to make amplitude variations, you need to look at the scalloping, and you need to look at the filter variations in GNU radio, and take all of those into account when you make the measurements. So that's about it for the presentation. We have a few minutes maybe for questions and answers.
Okay, thank you, Tom. Appreciate that. If you have any questions, you can open your chat window, which is along the bottom of the screen there in the middle, and type in a question if you would. And then Tom, if you open the chat window, you can see what they've typed.
Okay, I had to stop screen sharing to get the chat window to pop open.
Oh, great. No questions.
No questions.
Don't worry, I can jump in.
Okay.
Okay, Derek, go for it.
Well, first of all, thank you. This is good talk, and I've been working on a bunch of the same sort of things on and off over a lot of years at this point. And so it's great to see other people doing like noise figure measurements from within GNU radio. Have you automated any of that? Tried automating the noise source control?
Yeah, no, I have not. The noise source right now is a switch on the power supply. And so I haven't done anything to go put that out. I'm working on a project called Tangerine SDR. And on that receiver, we have a broadband noise source for each channel, and there's a relay on it. And that relay is capable of being exercised under software control. One of the applications for that is to measure noise figure, but another application is for radio astronomy, where you can look at, for example, a galactic noise source. And then by toggling that relay on and off, you can look at the noise from the galactic noise source and then the noise from the onboard noise source. And if the amplitude of the onboard noise source is well known and characterized, then that can give you a reference amplitude against which to measure the galactic noise and give you a fairly precise measurement of wideband noise of the noise source. So having that automated is very valuable.
Well, if you email me a postal address, I'll send you one of these boards, which is a USB 28 volt controlled noise source power supply.
Oh, excellent, excellent.
Because I got fed up with this exact problem and realized that these little noise sources, I'll pull up one of the commercial ones. Are you using a commercial noise source or a home built one?
For these tests, I used a home built one, which is produced by the Miami Valley VHF UHF Society. What's on Tangerine SDR is a Zener diode powered by a precision current source and then a resistive attenuator.
Okay. What sort of frequency range does it work across?
The Zener diode noise source goes up into the UHF band. So it goes from very low frequencies up to UHF. I modified it to extend the low frequency range of the noise source. It was intended primarily for 6 meters and above, and some 0.1 SMT caps in the right place got the bandwidth down to below a megahertz.
Nice. I've always been hoping that somebody would come up with an open source design for microwave band, gigahertz and above band noise sources, because they're not cheap. And they only fall off the back of trucks so often.
Yeah, the Zener diode is inexpensive. The limitation, of course, is the capacitance of the diode and the lead inductance puts an upper frequency limit of well below a gigahertz.
I wanted to point out the VectorSync does have a way of labeling the x-axis. Now, at least, I don't know what release that came in, but
Okay.
You can change the X labeling.
Okay. Yeah, on 3.8, I changed the labeling of the axis, but I couldn't find a way to make 1,000 represent 7.5 megahertz very easily.
There's start and stop values, and then it interpolates the points, I think, or it has a step.
Excellent. That's a great feature.
As a general shout out to everyone in the room, when you come across things and you're like, oh, I wish it did that, please tell us, because we're not psychic as much as some of the people on the email list think we are.
Yeah. So for the frequency sync, having a storage display where you could tick one of those, I think would be of value.
I've started writing up an issue for that, a feature request.
Okay.
So I was thinking, those displays are always kind of inspired off of oscilloscopes and spectrum analyzers, and just the save trace option. Yeah, that's technically that should be quite simple to add in. How long it'll take somebody to spend the weekend doing it is an open question. But if anyone wants to play around with some Qt code, I'd happily give them a hand with that.
Okay, excellent. I'm always amazed how much can be done within GNU Radio from a test point of view. when I did the ionospheric experiments, I completely mocked up a model of the ionosphere in GNU Radio for validating the algorithm. And then that turned out to be extraordinarily useful. So having the complete test bench capability built right into the program, I think is probably one of the very strongest features of GNU Radio.
Yeah, you're not alone in running that sort of setup.
Tom, I have a question. Do you have anything on GitHub that you share with people?
Sure. So my GitHub is GitHub. The username is Tom, Tom /McDermott with the camel cased mail. Tell you what, I'll just put it in
Put it in the chat.
yeah. And I've got the OpenHPSDR drivers for in GNU Radio. And whoops, I typoed GitHub. Okay, and so the drivers are there. There's versions for GNU Radio 3.7, 3.8, and 3.9. And I guess soon to be 3.10 when that comes out. And so if you have Hermes or a Red Pitaya, you can run that. Red Pitaya requires additionally an FPGA load that causes Red Pitaya to output OpenHPSDR format. But if you have that, you can use multi-channel receivers. And there's a lot of folks using that. It's seems to be pretty well used. I get a lot of feedback on it, which is good. So there have been a lot of corrections and enhancements to the drivers.
Richard has a question about noise sources.
Hi, Tom. Thank you so much for your presentation. That was just fantastic. I use video, but I'm sitting on a bed in the room that has AC. So, you know, so I'm just trying to slowly dip my toes into this sort of stuff. And I'm looking at eBay or RFBay, as some people call it. And I noticed there's noise sources that are, 32 dB or ENRs, sorry, ENRs of 32 dB or ENRs of 15 dB, ENRs of 5 or 6 dB.
Yeah.
Is that just a calculation thing? Does it really matter which ENR or for an independent frequency range? But
yeah,
does it necessarily matter? Go ahead.
Yeah, it depends on what you're trying to measure. And you can convert one to another pretty easily. If, for example, you have a 25 dB ENR source, just run that output through a 10 dB attenuator, and you now have a 15 dB ENR source. So at VHF and UHF, you'll tend to find noise sources in the 5 dB ENR range to be convenient, because you're typically trying to measure noise figures in about that range. And so it's useful. If you are trying to make HF noise measurements where the background noise might be 15 dB above the background noise, or you're trying to measure the noise of a galactic source, you'll tend to find that outputs in the 15 dB range tend to be convenient. If you have a noise output range wildly mismatched to what you're trying to measure, you may end up with a case, for example, that if you have a 50 dB ENR source and you're trying to measure the noise figure of a 6-meter preamp, you'll have a difficult time trying to measure the difference. You'll be out in the tenths of a dB up on the high end of the curve, and vice versa. If you have a 5 dB ENR source and your received noise figure is 20 dB, you'll hardly see any noise change whatsoever. So you tend to want the noise, excess noise, in about the range of the measurement you want to make.
Yeah, I'm actually thinking microwave, although that's a terrible word. I'm thinking X band, KU band, kind of stuff. Is there any advice on that?
Well, yeah, it depends on the noise figure of the receiver that you want to measure. So if you have an X-band receiver with 5 dB noise figure, you'll want your noise source in the 5 dB range.
Okay, thank you.
I have a question. Conventional receivers have an indication relative to S units. So
Mhm.
what is an S unit and how do we relate it to what you've presented today?
Yeah, an S unit is, I think I'm trying to remember, there's a conversion. S9 is, gosh, I don't remember off the top of my head how many, it's minus something dBm per hertz. And so I don't remember the factor right off the top of my head, but there, you can look it up on Google, and there is a conversion factor for S9 to dBm per hertz. And so from that, you can convert between the two.
Minus
Okay.
93 dBm.
Okay, minus 93 dBm per hertz.
Okay. Well, thank you very much, Tom. It was a very nice presentation. And in some number of days that will be published on YouTube, and I will put the link on the Talk Ham Radio page so people can see the finished product. And so barring any other questions, I think
Couple
we
of questions if you have time.
okay, go ahead.
Hi, this is David. Tom, I think I met you out in Dallas a couple years ago talking about Tangerine.
Okay.
Nice talk. Just a couple, actually just more of a comment talking through processing what I just heard in my mind, right? Your presentation is basically with a signal straight into the ADC, whereas I might be using an SDR with a preamp of some sort, right? Some sort of LNA. So, and
Right.
therefore, some of these concepts are sort of nonlinear or chopped, right? It's closer to a traditional amplifier on the low end, and then if you bypass or saturate, then you go through the ADC.
Correct. Yeah, if you drive your ADC anywhere near compression, then if you drive your preamp anywhere near compression, then you'll start to get analog-like odd order and even order products produced by the preamp.
Okay, and great. And then on your comments on the combiners, right, for the 2-tone measurements, you mentioned, or you seemed worried about crosstalk. So have you considered, say, like a 6 dB pad between the two generators or on each generator, just for some level of isolation or impedance matching?
Yeah, it's possible to do that. The problem I was running into is I was running out of signal level from the generators. And so if I padded them down to reduce the crosstalk, I reduced the dynamic range I was able to measure.
Gotcha. Okay. Yeah, and then your trade-offs between the different types was interesting. A group I've been working with had this conversation recently, which is a better splitter for different things. And if you know Goran Popovic, I believe he counterintuitively mentioned that the resistive splitters are best for noise. So I'm not sure if that was a consideration, but just thought I'd throw that out there.
Yeah, if you are in a range where noise is significant or resistor noise is significant, that could be a consideration. If you have extremely strong signals, the resistor noise is probably not significant. However, the way the generator acts to